Swayam Prabha. Digital India. Educated India.
Okay, so we have seen that materials are full of flaws. There are number of defects in the material in the form of inclusions, in the form of voids. So, metallurgical and non-metallurgical inclusions flaws are always present in the material, and this material is loaded either monotonically or in a fluctuating pattern of loading. So, what we have been discussing so far has been monotonic loading, and then we have seen that fracture can be either brittle or ductile depending upon the property of the material as well as the rate of loading. So, if the rate of loading is very high, then often you tend to get brittle fractures. So, under impact loading, the fracture can be different from that of slow loading under monotonic conditions. Now, another variety of loading which is of practical use is, or practical interest is that of fatigue loading. Fatigue loading means that there is a change in load, there is a continuous change in load as the product is used. For example, you take a boiler, you have heating and cooling cycles, you start the boiler, it works for a number of days, then it is cooled down for maintenance, again you pressurize it, it goes on for a number of days. So, here you are heating and cooling the boiler. So, you have thermal changes, temperature changes from the room temperature to its working temperature and back to room temperature, plus there is change in pressure also. That is, before loading, before getting to the operating temperature, it is let us say atmospheric pressure, but as you increase the temperature, the pressure inside the boiler continues to increase. So, now you have increase in load, increase in stress, retention of stress for a long time, and decrease of stress, decrease of load, and then it is back to room temperature and atmospheric pressure, and the next cycle starts when the boiler is further pressed into service. Similarly, you have in case of tools, you have tools like let us say forging tools or forming tools, where the tool comes into contact with the workpiece and the contact gets released. Again it comes into contact, it is loaded. So, the tool surface continues to get loaded and unloaded cyclically, and the number of cycles the tool can see can be as high as few hundred cycles per minute. So, the number of cycles can be as large as that, or they can be as long as in case of a boiler, where the boiler can go for number of weeks, number of months before it is shut down for maintenance. So, in fact, people would not like to shut down the boiler for years, because the act of or time taken to start the boiler and shut it down is so much that it is not affordable to do it very frequently. So, there are different time cycles, that is time duration of every cycle is different. For a boiler type of equipment it is rather long, for the tool type of equipment it is much shorter. We have bicycles, for example, you have a bicycle, and if you look at the wheel, then there is a point of contact between the ground and the wheel, and the load is transmitted to the ground through that point of contact. So assuming that the wheel is absolutely circular and it does not get flattened under load, you have a point contact with the ground, and that point keeps on changing. So as the wheel rotates, that point keeps on changing. So a point which came in contact now was loaded, then it went out of contact, therefore it got unloaded. So this way every point experiences loading, unloading type of cycles several times a minute, depending on the speed at which the bicycle is being moving. So there are number of situations where the fluctuating loads are or cyclic loads are imparted. Another example is that of a chair, where you sit occasionally. You sit on the chair carries your load, then you get up from the chair gets unloaded. So the interior parts of the chair which take your load are loaded and unloaded, but now there is no cyclic pattern of loading because you sit on the chair at your will, the chair gets loaded at your will, and it's not that only you sit on the chair, somebody else uses the chair, somebody else has a different weight. So kid sits on the chair, it will be much lower weight, an elderly person or a heavy person sits on it, it will have a higher weight. So the fluctuation in the loading and the time duration of every loading is uncertain. So then this kind of loading also leads to some kind of loading pattern which is quite random in nature. So if you look at the failure under fatigue, I mean finally every loading, monotonic loading or fatigue loading culminates in failure, but then the nature of failure is extremely different as compared to what we find in fatigue. In monotonic loading, what you find is either a ductile fracture or a brittle fracture, meaning either the fracture is intergranular or transgranular. Transgranular is usually found in ductile fracture, whereas intergranular fracture is the characteristic of brittle fracture. So that is what happens in monotonic loading. But now here you have fatigue where the crack does not propagate all at once. So if you look at this, so this is the origin of the crack, and then these are so called beach marks. These are called as beach marks because they resemble the marks you see on the beach. Now the marks on the beach are created by the waves coming onto the shore and going back, again coming back to the shore and going back. So these wave patterns are created on the sand, similar to what happens over here. So here there is an origin of the crack. The crack propagates a little in one cycle, it remains there, then depending on the load it propagates further. Now we have seen during our discussion on fracture that the crack propagates depending on the degree of stress concentration. The degree of stress concentration is high, the probability of crack propagating will be that much higher. If the fracture toughness of the material is high, then the energy that is the strain energy that is available for the crack to grow is absorbed by the plastic zone at the tip of the crack, and therefore the crack does not propagate any further. On the other hand, if the surface energy is quite low and so even with a small strain energy that is available, the crack will propagate very rapidly. So this is a typical, the second part is typical of brittle materials, and whereas here the crack is propagating not at once, but it's arrested at various times, because you load the workpiece, the crack propagates, then you relax the load, the crack gets arrested, again it propagates, again it gets arrested. So you have, since you have loading cycles, it's not monotonically loading, and again the load levels in particularly cyclic loading do not extend beyond the limit. So you have let's say cycles of 100 MPa. So you reach 100 MPa and come down to 0. Like in case of boiler, your circumferential stress, for example, might reach a certain value of stress when it is under operation, then it comes down to 0. Again it goes to 100 MPa or whatever stress it might be, and then it comes down to 0. So this way the stress in fatigue loading reaches a certain level and then gets relaxed. Well, in case of rotating bending type of fatigue of shafts, let us say you have power shaft which is rotating under load, there you will find that the loading changes not only from tension to 0, but it goes into the compressive direction as well. So, you have basically a loading characteristic where the load alternates between tension and compression. So, it all depends on the situation in which the workpiece is working. So, we have this fatigue crack which has been generated over here. In fact, there would have been a flaw over here, either a machine mark or a porosity, or that is a blowhole or a pinhole or something like that, or even an inclusion at which the crack could start, and then it propagates with every loading and unloading cycle. So, this fatigue crack propagation can be easily marked based on the striations, the so called beach marks that are generated on the surface. And then here, once the crack has propagated up to a certain distance, here you see the region of catastrophic fracture, meaning that the strain energy here is too much as compared to the surface energy that is needed to generate this surface, due to which there is a fast fracture, as it is called. It is called as either fast fracture or catastrophic fracture. So, this kind of fracture is can be intergranular or transgranular depending on the property of the material, but then this region is just unable to take the strain energy that is available with the crack that has advanced up to this point, and therefore, there is a region of fast fracture. So, in fatigue failures, it is easy to identify the location of the crack or the initiation of the crack, and the fracture surface typically at the origin here is usually smooth, because the crack originates either at inclusion or at the grain boundary. So, all these sources appear very smooth, whereas once it starts propagating, then you see the beach marks, intense beach marks which are present over here, which is a testimony to the fact that the material has arrested the crack time and again. So, the material has had the kind of fracture toughness which has resulted in arresting the crack. The crack has propagated not all at once, not in a catastrophic manner, but it has been arrested from one cycle to the next. So, the crack has been propagating very slowly from one cycle to the next. So, what it means is that when you are loading the workpiece, although things may not be visible from outside, the defect inside could be silently growing until the defect reaches to such a size that there is a sudden failure of the or sudden fracture of the workpiece or of the component in question. So, here what you will see is that nothing would be seen from outside, because crack is silently propagating inside with every fatigue cycle or every loading cycle, and then having advanced up to a certain extent, it will lead to a catastrophic failure. So, the consumer or the user is going to just see that the workpiece has fractured or the component has fractured all of a sudden. So, there can be multiple origins of a fatigue crack as well. So, you can have the initial origin of the fatigue crack in some brittle region, okay, and here there could be another fatigue crack which originated at some other point. So, this is a cross section of a bolt that was holding a seat in the airport. So, people come and sit on a seat which was meant for making the passengers comfortable, and that bolt suddenly gave way because the crack which was so this is the source of the fatigue crack. So, there is a fast propagation of the fatigue crack over here, another crack initiated over there, and then there is a fast fracture at the center, due to which the bolt snapped all of a sudden. So, essentially what happened was over a number of cycles of person sitting and getting up, sitting and getting up. Again, these cycles do not have a single amplitude, there is no upper limit as such, because different kinds of people different ages of people, different people of different weights come and sit there, and the bolt is subjected to fatigue of an unknown or unpredictable duration, unpredictable magnitude of cyclic loading, due to which there is fatigue damage which accumulates with every person sitting there and getting up. But then that fatigue damage remains silent, that continues to occur silently inside the bolt, and when the next person comes and sits, the bolt suddenly fractures, because now the fatigue crack which has grown up to a certain point is and another fatigue crack which also has advanced up to a certain limit results in a fast fracture of the remaining part of the bolt, and therefore the person who sits on the chair suddenly finds that the bolt has just given away. So here the fatigue is of a different nature compared to what we were discussing earlier, and so this is also a part of life where fatigue damage takes place very silently, keeps accumulating inside the material, and the final outcome is fracture which the person gets to see. And when it happens, it's very rapid, it's very fast, and therefore it happens without a warning. So these are the kinds of loading which we have seen. Here, as I was telling you, there is a cyclic loading from tensile to compressive. So you have tension at the top, compressive at the bottom. So if you take a boiler, for example, it will always have stress either here or 0. Again it gets stressed there or 0. It never goes into compression. On the other hand, the stress becomes compressive in case of, say, rotating bending type of fatigue, meaning you have a shaft which is rotating at a certain speed and it has got a load on it. So typically motor shaft, for example, will be subject to this rotating bending type of fatigue. So for that matter, any shaft, engine shaft for example, in an IC engine will be subjected to rotating bending type of fatigue. The crankshaft, so they are also subjected to rotating bending type of fatigue. So a number of fatigue cycles which are undergone by different machine elements. You take the connecting rod of a vehicle, connecting rod of a car, it undergoes not only tension compression type of cycles, but it also undergoes bending in different directions. So it gets bent in about 2 axes, and so the bending reverses direction, and therefore the connecting rod undergoes very complex state of fatigue loading during its operation. So here, for example, this is called as the mean stress, and this is the maximum and minimum stress. So this mean stress is midway between the two, and therefore it is sigma max plus sigma min divided by 2. The range is the overall range is sigma max minus sigma min, and sigma amplitude is sigma r upon 2, that is the range, half of that range. Okay, so amplitude is half of that range. So this is the amplitude of the signal of the loading, and this r refers to sigma min upon sigma max. So for example, sigma min upon sigma max, in this type of situation, sigma max and sigma min are numerically the same, but they are in different directions. So r is equal to -1 in this case, because sigma max here and sigma min here are numerically equal but different in sign, therefore it becomes -1. On the other hand, if you look at this kind of loading, you have the mean load. Okay, the mean load is somewhere in the tensile direction, and the range is sigma max minus 6. So the range is something like this, and so the amplitude, the overall amplitude is given based on this line. So sigma min line is on the tensile side. So there is a constant tension in the on the means level. There is a constant tension, and there is some mild compression to which the material is being subjected to. So, let us say that this point rises right up to here, up to 0, then you will get and then this comes here, and then the cycles are something like this, where you have, it starts with 0, goes to a maximum, comes back to 0, again goes up, comes back to 0, again goes up. So, maximum is at a operating pressure, minimum is at atmospheric pressure, and this continues over a number of periods of time in number of cycles. So, this kind of cycle is experienced by a boiler type of an equipment which we have been discussing, where R is sigma min upon sigma max. So, sigma min is 0, sigma max is the operating corresponds to operating pressure, and therefore, this R is equal to 0 over here. So, if R is 0, so that is a typical boiler type of cycle, but then there are other situations where the stresses are mildly compressive in nature. So, they are not, the tension and compression does not alternate to equal magnitudes, the tension is much greater than the magnitude of compression. Okay, right. So, that is how you have different values of R characterizing the nature of the cycle, the nature of the loading. So, some cycles can continue in the tension zone, some cycles can always be in the tension zone, and so their R will become R will always be positive. So, when R is more than 0, you must understand that sigma min and sigma max both are in the tensile region. R being negative means that sigma min is in the negative region. So, you have some compressive stresses coming into play, and if R equal to 0, naturally you can assume sigma min to be 0. Now, this is the typical cycle, undefined or unpredictable cycle. So, there is no pattern as such in this. So, this is the typical cycle characterized by the by chair or furniture being placed at various locations. So, if you have I mean, a person sits and he gets up, sits, gets up, but then again there is no reason why the stress should go into compression. So, naturally again here the cycle will have to be ending at 0 here. So, 0 point should be somewhere here, so that the load goes up, comes down, then again goes up, it comes down. Maybe the person has kept some luggage here, the person got up but has still left the luggage behind. So, there is still some weight being kept here, although the weight has decreased. So, these are basically fluctuating loads. Not at all times does the load come down to 0, but the load continues to fluctuate in a cyclic, not exactly in a cyclic manner, but in a certain pattern. So, if you look at fatigue stress cycles which are regular in nature, we can have either a situation where sigma mean is equal to 0. So, you have amplitude is fixed, amplitude in compression and amplitude in tension is the same. Here the amplitude in tension and amplitude in compression are different, and therefore, the mean is in the tensile side, and so you have very slight entry into the compressive region. So, there the stress is for a small duration, the stress is compressive, but then largely it is tensile. So, sigma m is in towards the positive direction, but then R is still negative, R mean. So, sigma mean is negative here. So, R is still negative. In this case, everything is in tension. So, here you have the minimum stress is under tension, maximum stress is under tension. So, the entire component is subjected to tension at all times. The only thing is the tension is fluctuating, that is about it, but the tension remains at all times. So, there is minimum tension, maximum tension, and there is a mean tension being experienced by the material. So, what we find is that in this fatigue loading, the there is no way that material there is no occasion for the material to get into a compressive regime. So, what we what we calculate or designate as a probable stress amplitude, okay, which we can possibly have, is given by the desired fatigue strength into 1 minus sigma m by sigma Ts. So, what it means is that if you have a certain fatigue strength of the material and you have certain tensile strength of the material, that is ultimate tensile strength. Now, if your mean stress is on the tensile side, then there is hardly any room to have any stress amplitude, any room for a large magnitude of stress amplitude over here. So, for example, if you have certain fatigue strength and you have the so this is and you do not want it to reach the ultimate tensile strength. So, the range between the mean stress and ultimate tensile strength can be the maximum range of amplitude that you can possibly have. So, when the amplitude becomes equal to the tensile strength, so as the sigma amplitude becomes sigma Ts tensile strength minus sigma m. So, if this is tensile strength, okay, if it is tensile strength and this is the sigma mean. So, this is the stress amplitude you can possibly have, right. So, at that time the corresponding sigma Fs can be determined from this kind of formula. So, sigma Fs desired fatigue strength is for a 0 mean stress. So, it is for this type of condition. Sigma A is the feasible stress amplitude. So, it makes sense because if you have sigma m equal to 0 and sigma A is then the sigma Fs. Sigma A is the sigma amplitude and sigma Fs is the desired fatigue strength. And so, if sigma m is not very close to sigma Ts, if sigma m is essentially equal to 0, then your sigma amplitude can be very close to sigma Fs. If sigma m is very close to sigma Ts, if sigma m is as you see here, it has gone up and it is approaching sigma Ts, then there is a risk that your sigma amplitude might have to be 0 altogether, because as sigma m approaches sigma Ts, then there is uniform load or time independent load. So, the load is applied and it persists for a long period of time, because it is very close to the ultimate tensile strength. So, there is no room for any kind of fluctuation that can be accommodated, because you would reach the you would reach the tensile strength and the failure will take place purely because of that. So, what it means is that if your sigma m is 0, something like this, then there is room for you to have the amplitude equal to the desired fatigue strength. Otherwise, if sigma m is very close to sigma Ts, then this does not affect the sigma A, it is exactly 0 because of this term, right. So, as the mean stress increases, the stress amplitude must decrease in order for the material to withstand the applied stresses. So, this is called as a Goodman relationship. So, as you increase this, this sigma A continues to decrease. So, if you plot mean stress against the stress amplitude, you will get a line that decreases, that is called as a Goodman line. Now, if you have fatigue damage taking place in a rotating bending type of fatigue. So, this is the kind of fatigue cycle that is in rotating bending, because you have when you rotate something and it is being bent, the outer fiber goes into compression for a while and then it comes to the other side. So, once the shaft rotates by 180 degrees and then it comes to the tension, again it goes to compression and so on. The tension and compression have the same magnitude, and therefore, the same magnitude of stress is experienced in both tension and compression. So, R becomes equal to -1, and so the rotating bending fatigue has the stress amplitude with number of cycles to failure as something like this. So, beyond a certain limit, beyond a certain number of cycles, the stress amplitude becomes independent of the number of cycles. So, basically what it means is that if your loading becomes lighter and lighter, then the material will withstand, or the fatigue crack will not propagate at all. I mean it might get permanently arrested, and therefore the sample can withstand those fluctuating loading for infinite number of cycles, forever. This is understandable because I told you that for a crack to propagate, you need certain amount of strain energy, you need certain amount of strain energy to overcome the surface energy that is required to propagate a crack. Now, if the loading is very light, because loading is the driving force for the strain energy to get generated. Now, if this driving force is relatively small as you reduce the load, then there is just not enough stress, there is just not enough strain energy for the crack to propagate. Naturally, the crack will remain at the same size and will be there forever, retaining the same size, because at no point is the strain energy going to exceed the surface energy that is needed for propagation of the crack. So, for infinite number of cycles, the crack will remain in its position, the defect will remain in its position at the size to which it might have grown, and it will propagate no further. On the other hand, if you look at this leg, because the load is high, so the stress amplitude is high, and therefore the fatigue limit is relatively smaller. So, here the failure takes place at a lower fatigue limit. That is because now the stress being high, the strain energy is high, and therefore the fatigue damage that gets accumulated also is high. Another feature of fatigue is that some Bauschinger effect comes into play, in the sense that when you subject a material to tension and compression, that there is softening of the material. So, what it means by softening is that when the loading changes direction from tensile to compressive, then the dislocations which get piled up being stressed in one direction suddenly experience a change in direction of loading. So, dislocations are able to move very rapidly. The dislocation movement becomes possible at a much lower stress when there is a change in the direction. So, these are basically a transient phenomenon. So, Bauschinger effect is a transient phenomenon that occurs when the direction of loading is changed. So, right from tension to compression, the material behaves soft in a transient manner because of this change from tension to compression has taken place. Now, because of this transient softening, the load which is already acting on the material manages to generate certain amount of strain. So, this way the fatigue loading tends to accumulate this strain during rotating bending, and so this accumulated strain can also result in accumulated fatigue damage. So, that is the reason why, as you increase the stress, the stress amplitude required for damage decreases. So, for higher stresses, the number of cycles of fatigue damage are lower. When the stress decreases, the strain is also reduced, the plastic deformation is reduced, and this fatigue limit essentially could lie within the elastic limit. So, this fatigue limit, the stress corresponding to the fatigue limit would make sure that the material is not stressed beyond the elastic limit or the yield point. In the high stress amplitude case, the material can get into the plastic region, the plastic deformation can take place, and therefore it is called as low cycle fatigue, meaning that the number of cycles withstood by the material under fatigue are very low. So, this happens at a very high loads which exceed the plastic deformation. So, usually in low cycle fatigue you have plastic deformation. Plastic deformation leads to accumulated strains, as I just explained, and these accumulated strains result in accumulated damage, and then the crack propagation becomes easier, and therefore the final failure under fatigue cycles is it happens at a much smaller loads. Now, if we start reducing this load to smaller and smaller plastic strains, or smaller and smaller loads, which means that the loads are slightly in excess of the yield strength, right. Here, for example, load will be far in excess of the yield strength, but here the magnitude is so small that the material might not exceed the yield strength by a great extent. Then the plastic strains are also that much lower, and therefore the ability to withstand the cyclic loading is higher. And then when you come within elastic loading limit, then there is absolutely no issue. There is no crack propagation as such, because when you have in the elastic loading the cyclic stress, then what happens is the growth of defects is extremely small. The growth of defects is extremely small, and therefore it can continue to right up to failure. And so that is the reason why this line becomes absolutely horizontal, independent of the number of cycles to failure, and this is called as the endurance limit. So if anything is designed for infinite fatigue life, as it is called, then you take the working stress to be this so called fatigue limit. So this is the maximum stress to which you should subject the material to, so that it withstands stresses for lifetime. With a factor of safety, you can always be sure, or you can almost be sure that it will last forever without having to be replaced. So when we talk about fatigue damage, you have some immunity from fatigue damage or fatigue failure when you have the stress amplitude which is lesser than what is given by this line. So some kind of immunity can be enjoyed by the designer from any fatigue failure. So here you see that you have low cycle fatigue where the plastic strain is involved, and number of cycles are 10 to the power 4 to 5, whereas in high cycle fatigue the number of cycles are much greater. So this is why this so called SN curve, that is the stress amplitude to the cycles to failure curve, are used for designing shafts which will withstand a large number of cycles, particularly motor shafts which require very high level of reliability. They need to, one has to be sure that they will serve for the entire lifetime, right. So that is the reason why this SN curve is always consulted when one designs shafts for fatigue damage. Now these fatigue failure curves are probabilistic in nature. So if you test different samples, a large number of samples which are subjected to given conditions of loading, given number of cycles, then you will find certain samples fail below the so called fatigue limit. Most samples fail above that fatigue limit. So basically you draw the fatigue limit based on the probability of failure. So you can have different SN curves for different probability of failure. So if you want high reliability, you can have SN curve corresponding to 0.1, that is 10%. Here it is 1% probability of failure. And if you want to be even more conservative, even more safe, then you can draw another curve which is lower than this, so that probability of failure is practically 0. So now if you look at the SN curve, let us say you take a curve where probability of failure is 0.5, 50-50, and then you apply factor of safety to it, probably you can be lower than the SN curve corresponding to probability of 0 failure. So that is why instead of determining a number of curves based on probability, one uses the a curve of say 50% probability and then apply factor of safety, so that you are sure that failure is not going to take place once you have used a stress value corresponding to infinite fatigue life, right. So here what you see is the crack initiation, crack propagation and final fracture. So at every beach mark over here, you see that the crack has propagated incrementally. So there is an incremental crack propagation taking place, okay, and the crack which would have nucleated at surface scratches, sharp fillets, keyways, or any sharp changes in cross section, sharp corners. So this is where the stress concentration takes place and the crack nucleation takes place. So the crack nucleation sites are the ones where there is a significant amount of stress concentration. So average stress is far lower than the local stress that is experienced at the base of the scratch or base of the notch. So keyways, threads, dents, so these serve as crack nucleation sites. Sharper are the notches, sharper are the scratches, you will find that the crack initiation is that much faster, crack propagation is also that much faster because of a much greater stress concentration taking place, the much greater stress ratio, that is local stress divided by the average stress. So you see another figure over here where the origin of the crack is here, and you see that the crack is advancing towards the center. So cyclic loading can produce microscopic surface discontinuities resulting from dislocation slip. So we know that plastic deformation requires dislocation slip, and so when you see beach marks, it means that the crack has been arrested by the plastic zone, again it propagated, again it got arrested, again it propagated, and so on. So these are the discontinuities resulting from dislocation slip steps that might also act as stress reserves and therefore as crack initiation sites. So you have a number of attempts by the material to arrest the crack. Had it been brittle, there would have been no beach marks, there would have been no arrest of crack, it would have just propagated very rapidly. But because the material is ductile and being subjected to cyclic loading, it is able to resist the advancement of crack, because load does not remain at the same level all the time, the load momentarily goes to a very high level. So the crack propagates by an increment, the load goes down and therefore the crack propagation is arrested, again the load goes up, again there is an increment, and this way particularly when the load goes into the plastic deformation regime, there is dislocation slip taking place due to which some local plastic deformation would take place at those locations. The region of a fracture surface that formed during crack propagation step may be characterized by two types of markings termed as beach marks and striations. So striations and beach marks are slightly different in nature. So let us see what the differences are. So you have here the region of initiation of a crack, that is origin of the crack over here, okay. Usually maximum stress occurs at the surface, so that is the reason why the cracks also originate at the surface. Most of the defects like machine marks or notches, they are also on the surface. So usually more serious defects are at the surface. Interior also you could have defects, but more defects occur at the surface, more glaring defects occur at the surface, and due to which the failure is likely to take place from the surface. So the origins of the crack usually are on the surface, and then it starts propagating inwards. So most cracks leading to fatigue failure originate at surface positions, especially the stress razors. For example, here you have a stress razor in the form of an abrupt change in cross section. So at this corner you would expect the stress concentration to take place and crack to start. Now this is because when there is plastic deformation and the material is being subjected to repeated cycles of plastic deformation, the residual ductility of the material gets exhausted over a period of time, and then wherever the stress gets concentrated, you have significant amount of plastic deformation taking place with every cycle. This accumulated deformation exhausts the ductility, and at some point you have a origin or initiation of the crack. So origin of a crack is either on the surface at a highly stress concentrated region where there is either abrupt change in the cross section, or there is accumulation of plastic deformation, or the ductility is exhausted, and then the crack starts. So this is how the cracks originate, and then they propagate due to fatigue. So you can easily have these small scratches during machining operations, and in this case the crack is formed at the top edge. The smooth region near the top corresponds to the area over which the crack propagated very slowly. So this is the region where the crack propagated very slowly, being arrested from time to time, and then this is the region of fast fracture where the crack dissipated all the energy in different directions, and the rapid failure shows that so the dull and the fibrous texture. Being a ductile material, although the fracture took place at a fast rate, still the nature of the fracture was ductile, being intergranular fracture. But then it is fast fracture because it happened at a very rapid rate. The energy was dissipated, the strain energy was dissipated at a very rapid rate. Now if you look at the surface, many times in order to prevent the crack from forming, people usually take care to make the surface stronger, because more is strong is the surface, lesser is the likelihood of origin of a crack. Like there is lesser probability or lesser chance that a crack will originate at the surface. So that is why people case carburize. So people increase the carbon content locally in an attempt to generate high strength at the surface. So now at the surface the material is strong, interior the material is soft. The strains or the stresses are very high at the surface, the stresses are relatively low in the interior. So you have certain thickness up to which the hardening has been done. So the chemical composition at the surface has been changed to a high carbon chemical composition, whereas the relatively lower carbon composition is present in the core region. So this is the kind of case carburized region. Similarly, if you increase the nitrogen content or nitride formation, then again you have a higher strength of the surface. So what happens is for nitriding, nitride forming elements like chromium, aluminum, so these are added to the material, so that on the surface when you subject it to the nitriding treatment, the nitrogen diffuses through the surface and forms aluminum nitride and chromium nitride, thereby giving a large amount of strength to the case. Interior is soft. So many times during fatigue loading, what happens is the strains experienced here are relatively small. That is because of a very high load withstanding capacity of the case. the core is relatively soft, it is capable of undergoing large amount of deformation, and therefore at the interface now you have a discontinuity, because at the interface now on the case side there is very little deformation, on the core side there is large amount of deformation, and therefore most of the damage gets accumulated at the interface between the case and the core. So, the case thickness is something that is a matter of design. So, if you have to avoid fatigue damage, if you want to minimize cumulative fatigue damage, then a sufficiently thick case is necessary, so that the material at the case remains at high strength and it withstands most of the loading conditions. So, if you look at this, sigma m3 is if you look at the stress amplitude, if the mean stress is low, the stress amplitude is smallest, and m1 is the least of the mean stresses, sigma m is least of the mean stress, and the stress amplitude therefore can be much higher. So, if the sigma mean is lower, then the stress amplitude is the maximum. So, sigma m1, so corresponding to sigma m1, which is the lowest of the stress mean stress amplitudes, the overall stress amplitude, the maximum stress amplitude, that is sigma a max, can be higher for a lower value of sigma m, that is mean stress. Besides, as the number of cycles to failure increase, your the stress that is tolerated by the material has to decrease, even the mean stress has to decrease. So, what this means is that when the material is subjected to fatigue loading, if you want to get the material to withstand infinite life, then even the sigma mean has to be sufficiently low. If the sigma mean is high, then it is going to be very damaging because of its capability to deform the materials, and that is why the stress amplitude is low, and so is the mean amplitude or mean value of stress that the material can withstand. So, if the sigma m3 is the highest mean stress, and the amplitude continuously decreases with the highest, even if the stress is high, the amplitude with number of cycles continues to decrease. So, as the stress amplitude decreases, your life increases. So, basically if you want your product to survive longer, then light loading is the only answer to it. Another way of doing it is to induce what is called as compressive residual stresses on the surface. Now, tensile residual stresses we know are highly damaging, because the residual stresses get added up to the applied stress and therefore reduce the load carrying capacity or the stress carrying capacity of the material. On the other hand, the compressive residual stresses enhance the load carrying or stress capacity, and therefore, even if you have subjected the material to high levels of stress, a compressive residual stresses will make the material behave as though you have subjected it to a very low stress conditions. So, this sigma m3, even if you have a large mean stress, still you will find that the magnitude of stress that is possible, the stress amplitude that is possible is much higher compared to when residual stress is 0, because the compressive residual stress partly nullifies the tensile nature of the stress amplitude that you might have applied. So, that is why this is short pin, meaning the ones where compressive residual stresses have been induced onto the surface, it has got a stress amplitude which is much greater as compared to the normal situation. So, for given cycles to failure, the short pinned or the surface where the residual stresses have been induced, compressive residual stresses have been induced, you will find that the stress amplitude tolerated for infinite fatigue life are much higher. So, the stress amplitude that is tolerated is much higher for infinite cycles to failure. So, short pinning means that you induce residual compression. What does short pinning do? When you bombard the surface with steel shots, so you have balls of steel, or you have balls of tungsten carbide, you have balls of silicon carbide. So, there are different ceramic materials with which the ball is made, and then these are hammered, or these are shot at the surface. So, they impact the surface and create small indentations. So, basically what they do is that they increase the surface area. So, because of the indentations which are created adjacent to each other, the surface area tends to increase, right. The surface area tends, when it increases, so it is a permanent deformation. So, the surface area is increased permanently, and when the shot has done its job of increasing the surface area and the load is released, because the shot will impact. So, when the shot impacts, the surface area increases due to plastic deformation. When the shot moves apart, the surface gets unloaded. Now, when the surface gets unloaded, the material locally tends to come back to its original position, but the fact that the shot has increased the surface area, the indentation of the shot, indentation by the shot impinging on the surface has increased the surface area. The increased surface area cannot be pushed back to its original value. Naturally, what happens is that the surface compression, the compressive stresses are created on the surface, because now the material tries to pull the surface back to its original surface area, but the material refuses to come back, and therefore, these are so called unreleased elastic stresses which remain behind. These unreleased elastic stresses are compressive in nature. So, you have a short pinned surface which has having a compressive residual stress present. So, the extent of indentation, the speed or the velocity of the balls, the amount of energy that is transmitted into the workpiece for plastic deformation, all govern the amount of indentation or the depth of indentation that is made by the shot, and therefore, the residual stresses being induced by this process on the surface. So, that increases the so if you look at the hardness is much higher on the surface. It is made out by the smaller indentation. So, loads are the same, but indentation is small on the hard surface as compared to the soft interior, where the indentation is much bigger. So, you see that case carburizing, case nitriding, or surface hardening treatments, any other surface hardening treatments resist crack initiation, and in addition to that, if you are going to short pin the surface, it will relieve tensile residual stresses, and it will also generate compressive residual stresses on the thin outside surface layer, resulting in a very good fatigue life, an increase in fatigue life. Now, together with this, there is another kind of fatigue damage, which is thermal fatigue. Now, in case of boiler, about which we were discussing earlier, there is thermal fatigue. In addition to that, there is mechanical fatigue arising out of fluctuations in pressure, fluctuations in temperature, and then add to that the corrosion taking place from time to time. That is because the water inside the boiler has got a certain pH. It is usually not exactly 7. It may be slightly acidic, slightly basic, but then it is not exactly 7, due to which very small amount of corrosion could also take place. Now, what happens is, wherever the stress is more, the corrosion attack is that much higher. When the stress is low, the attack is relatively weak, or the attack is ineffective. So, that is why many of the machine elements which are subjected to fatigue damage are subjected to not only the kind of mechanical fatigue damage, but also to thermal fatigue damage and corrosion fatigue damage. So, that is something we must understand and take into account. This, for example, is an example of a compressor blade of an aero engine, and the compressor blade failed or it fractured. Now, if you look at the edges, the edges are also damaged. So, the blade edges have got damaged because of let us say air particles or basically wear and tear taking place in the material, and then the blade finally undergoes fracture, right. So, on the convex surface you have a lot of damage taken place, you see damaged blades, and here you see on a concave surface the damage plus the nature of fracture of the blade. So, this is a high pressure compressor rotor. So, you know that the compressors have different stages. So, you have low compression stage, high compression stage. So, this one is a high pressure compressor rotor, which means that the pressure acting on this rotor blades is extremely high, due to which the cantilever, I mean the blade is mounted in the form of a cantilever, and that gave way because of this high pressure loading plus the fatigue damage that had been created. So, the failure took place after 12.5 hours of running. Actually, when we take an aero engine, 12.5 hours is nothing, but then it failed. RPM is 103% of the RPM of high pressure spool, and material was BT6 titanium based alloy, the chemical composition of which is given over here. Now, typical BT6 alloy has got this chemical composition as the standard composition, ideal composition. The actual blade that fractured has this composition. So, you see that the chemical composition was absolutely fine, because it is well within the specified ranges, and therefore, the conditions of failure do not seem to have originated from a faulty material. So, material is not at fault. So, there are certain conditions which might have led to the fault. Now, here you find that there are no significant mechanical stress raisers, because there is no abrupt change in concentration stress due to which stress concentration can be suspected. But then there is a origin of the crack which is found to be here, and if you look at the fractographs, you will find that the fatigue crack, it was a fatigue crack which got generated, and it propagated very slowly in the form of striations. We will get into deeper into these this discussion in the next class, and continue our understanding of fatigue damage, accumulated fatigue damage, and how the fatigue failure takes place. Thank you.